Get started for today. So you should have handed in homework 3 in the back, and we also have your graded homework 2s for pickup. All right, so where we left off on Wednesday, we were talking about how to train decoders, given that we have observations of both kinematics and neural activity. And so when we have the monkey performing his reaching task, we're recording his hand position at every, say, 60 hertz. Every 16 milliseconds, we're recording his hand position. And at the same time, we're simultaneously recording his neural activity. And so for the rest of this class, his kinematics will be these variables, the xk. And for this lecture, xk is just going to be the velocities that we decode. So there'll be the x velocity at time k and the y velocity at time k. And so this is literally at every single time point, what was the monkey's arm reaching speed and direction. And at the same time, from his Utah electrode arrays that we have implanted, we'll have his neural activity. And for the rest of this lecture, we'll just assume, so yk of 1 here is the bin spike counts of neuron 1. Yk of 2 is the bin spike counts of neuron 2, all the way down to yk of n. And this is all at just time k. And we'll have 96, n equals 96 electrodes. That's the number of channels on our Utah array that we record from during these experiments. And so if you'll recall, we had our population vector. And at the end of last lecture, we were saying, well, this population vector has an awful lot of parameters. And so there are n neurons. There are 96 neurons. But then for each neuron, we have to fit one of their preferred directions. And this step requires interpolating a cosine and finding all these different parameters of this cosine function. We have to find these bi's and these alpha i's, again, 96 of them, one for each neuron. And then we have to find the scale parameter c. And so that's a lot of parameters to fit separately. And so what we wanted to do is we wanted to write this as just a single matrix equation, this xk equals L times yk. And our goal would then be to just solve for L. Why can we do that? Because when we had the monkey reaching, we knew his velocities, the xk, and we knew the neural data, the yks. And so we have observed everything in this equation except for the L. And so today in lecture, what we're going to teach is how do you find this L, given that you've observed both the monkey's reaches, these x's, and the monkey's neural data, these y's. And it turns out that this is going to be pretty simple with linear algebra. And in general, when we look at problems when we want to build decoders, we're always just going to want to get them in this form, x equals ly, because it's an equation that we know how to solve very simply. And so our first step is going to be to rewrite this population vector formula in this form, x equals ly. And so the first thing that we can do is, let me get a laser pointer. The first thing that we're going to do is we're just going to write this as a matrix multiplication. And so I'll take this multiplicative constant c over n and plop it down here. And then all I'm going to do here is separate the d sub i's, the preferred directions, and the factor with the neural data, these yks. And so all I've done is said xk here is equal to the product of these two of this matrix and vector. So d1 times y1 minus b1 over alpha 1 will give me this first term when I equals 1. And then d2 times y2 minus b2 over alpha 2 will give me the second term here when I equals 2. And we'll sum them all together. Does that make sense to everyone? So can someone tell me what the dimensionality of this matrix right here is if n equals 96? Anjali? Oh, sorry, I thought you were raising your hand. So we know that this vector right here has a bunch of numbers going from y1 to yn. So this is a 96 by 1 vector. And we know that our kinematics are what dimensionality. So here we're just decoding x velocity and y velocity. Yeah. So it's a 2 by 1 vector. And so that implies that this matrix here is 2 by 96. And does this make sense? It does, right? Because the di's are these unit vectors in 2D space. And so, for example, if your preferred direction, again, was just up and to the right, then this d sub I would equal 1 over root 2, 1 over root 2. So all of these d sub d raised to the I are just 2 by 1 vectors, and we have n of them. So this is a 2 by 96 matrix. All right, so we're not quite in the form x equals L times y yet, but we can start to now simplify this. So the next thing that we can do is we can take out these multiplicative constants and put them into this matrix, right? Because d1 times this term would be the same as d1 over alpha 1 times this term, no longer with the alphas. And so all I've done is I've taken the multiplicative constant and I've put it into this matrix. All good? So now the next thing that we would want to do is we would want to remove this constant because this constant here, because we want to get just this vector here to be simply the y's. And so to get this constant out, what I can do is I can take this matrix here with this constant and multiply it against the y's and then distribute it and then multiply it against the negative b's. And so concretely, that would look like this. And so b plus bpv, this term bpv, is merely equal to this matrix, C over n times d1 over alpha 1, et cetera, times multiplied by all the b's. And so all I've done is I've distributed this matrix across my differences here. Does that all make sense? All right, so if I were to just stop at this point, we would have an equation that looked like x hat k is equal to L times y k plus b pv. And so we're almost there, but we still have this constant that we have to get rid of. Does anyone have an idea of how we might get rid of this constant?
Add 1 to the y vector and the constant.
Exactly. So we're going to use our little trick from the last lecture when we were doing this kinematics example where we had a 1 in our vector of our state. And so what Nahal said was, we'll just add a 1 to our vector of y's here. And then if we put bpv in this matrix, then we'll see that it all works out because we have the dn's times the yns, which will give us the sums here, excluding the bi's. And then the bpv will multiply this last term 1. Is that clear to everyone? All right. So in total, what we've done now is we've taken this this sum equation, and we've written it simply as a matrix. And what's the dimensionality of this matrix now? Yep, 2 by 97 times a 97 by 1 vector. And so this equation here is exactly our x hat k equals L times our y tilde k. All right, and just to recap, our y tilde k is a 97 by 1 vector. Our L here is our 2 by 97 matrix. And our x hat of k is our 2 by 1 vector. And so when you guys work in homework 4 and in homework 5, you are actually just going to be building these vectors of bin spike counts, where you'll count the bins in some window. We'll call it 20 milliseconds for the rest of this lecture. And you'll be also calculating your velocities every 20 milliseconds. And that'll give you both these xk's and these y's. And so now we get into the more machine learning part of things, which is, given this equation, how do we find this term L? And so we have that this equation, xk equals L times yk, which represents our population vector, should first hold for all points in the training data. And so what do we mean by this? Well, when we start off the day, we'll have the monkey performing his reaches, and every 20 milliseconds, we'll sample both his velocities. So his velocity at time 20 milliseconds is right here. And his velocity at 40 milliseconds is right here, and so forth. At the same time, what we'll do is we'll have the bin spike count. So we're going to bin the data, and this y of 1 corresponds to the binned neural activity across all of your neurons from 1 to 20 milliseconds. So how many spikes occurred in every single channel over this window, 1 to 20 milliseconds. And then y2 would be the bin data from 21 to 40 milliseconds. And so over the course of the trial, we would record activity for 10 minutes, about 10 minutes. That's the amount of data that you'll work with in homework 4 and homework 5. And so we have a ton of these bins, thousands, if not tens of thousands of these bins. And what we want is that we want this L matrix, which relates the neural data to the kinematics, to hold for all of these points. Now, can we find an L that satisfies all these equations? I see some people nodding no. Why is that the case? So how many parameters are in this matrix L? How many unknowns do we have to fit in this matrix L? So the number of unknowns in the matrix L is simply the number of elements in it, right? Because in this matrix L, we'll have 2 columns, and we'll have, 2 rows and 97 columns. And you'll remember that inside each of these rows and columns were terms like D1 over B1, or alpha 1, times C over N, and there's a BPV over here. And so all of these terms, we don't know. And so for this L matrix, we have 2 times 97. That is 194 terms in this matrix that we don't know. So there are 194 unknown parameters. Is that clear to everyone? All right, so let's say that we recorded time. We recorded the monkey reaching and his simultaneous neural data, and we have k equals 10,000 time bins. And so this means that we have 10,000 times 20 milliseconds. And so I think that's 200 seconds of activity. And so here we'll have 10,000 equations, and we'll have to find 194 parameters that satisfy these 10,000 equations. But in general, this is what we call an overdetermined system. This simple L here that maps y to x can't hold for all 10,000 of these equations. So in general, this L doesn't exist. However, you can bet that because we have so many observations, we have 10,000 observations, what we're going to be able to do is we're going to have a lot of data to get L to be as good as possible. Okay. Is this making sense to everyone? Is there any part of it that anyone wants me to go over again? All right. All right, so what I can do is I can just consolidate all of the kinematics, the velocities that we have observed across all time, call it x1, x2, all the way up to xk. Yes?
So just going back to that.
Yeah.
Does this have anything to do with the rank of the matrix at all?
Excuse me. It does in some settings. So in this class, we're going to just assume that all of our matrices are full rank. And so if L had some rank constraint on it, then that would affect our learning. And if this isn't making sense, then don't worry about this. All matrices in this class will be full rank. And so when I construct this matrix here, where I've just concatenated all the time points, this matrix will be full rank, this L matrix will be full rank, and these Ys will be full rank. All right, so what is the dimensionality of this? And so what I'll do is I'll write this equation where I concatenate all of these xk's, and this equation where I concatenate all these yk's, and we'll see that this holds, right? All this is saying is that x1 is equal to L times y tilde 1, x2 is equal to L times y tilde 2, etc. up to xk equals L times y tilde k. So we've just written very compactly our k equations. And I'll just call this very big matrix x, and this very big matrix here y. So what are the dimensionality of these matrices all here? X is two by k, yep. And L is 2 by 97, I heard it. And Y is 97 by k. Great. And so these X and these Y matrices are very, very big, or they're very, very fat. They have 2 by, say, 10,000 time points. So this is a 2 by 10,000 matrix. This is a 97 by 10,000 matrix. And because we've observed the monkey's velocities and the corresponding neural activity at every single time point k, we know exactly what this X matrix is, and we know exactly what this Y matrix is. They were given to us by this experiment. And so now that we know what X and Y is, all we have to do is just find L. And so this is a little note related to the question just asked. In this class, we're going to assume that all matrices are full rank. Now, there is something called the matrix inverse. And if you haven't had linear algebra, the matrix inverse just means that if I have a matrix A and I multiply it by its inverse A negative 1, this is equal to the identity matrix. And the identity matrix is a matrix that just has 1s on all of the diagonals and 0s everywhere else. And this is just the linear algebra extension of 1. So it's the unity multiplier. And so if A's were scalar, we would, of course, have that A, the inverse of A is just 1 over A. And this is equal to 1. And so if you made that high dimensional, you would just get exactly what we have in matrix algebra, which is the inverse. And so you can think of this A negative 1 as sort of like a scalar 1 over A. And so what we really want to do in this equation is we want to calculate that L is equal to X times the inverse of Y. But we have a problem here because it turns out that you can only invert a matrix if it's full rank, which we said it is, but also if it's square. And so the matrix Y isn't square because we know that it's 97 by k, and in general, k is much larger than 97. K is something like 10,000. And so we're hitting a snag here because now we can't invert this Y, even though if we could invert this Y, then we would very naturally get our solution. So the way to get around this is to realize that Y isn't square, right? Y is a fat matrix, but Y transpose is. So what is the transpose of a matrix? If I have a matrix A and I take its transpose, then all I'm doing is swapping the rows and the columns. And so if I had an element, if I had a matrix that looked like 1, 2, 3, 4, 5, and 6, its transpose would be 1, 2, 3, 4, 5, and 6. And so all I've done is I've taken the element in, let's look at this 2, in row 1 and column 2. And I've said, now put it in row 2, column 1. So I've just swapped the column and the row dimensions. 4 is in column, that's not it. 6 is in row 3, column 2. So now it should go in row 2, column 3. And so that's all we mean by transposition. And so if we have y, and it's a a 97 by k matrix, when we take y transpose, that'll turn out to be a k by 97 matrix. Does everyone see how that is? So now if I take y and I multiply it by y transpose, then I get that y transpose is what dimension? Great. So y transpose is now a square 97 by 97 matrix. So all I'm going to do now is I'm going to take our equation x equals L times y, and I'm going to do something that we can always do, multiply it by the same thing. So I'll multiply the right side by y transpose, and I'll multiply this right side by y transpose. And now at this step, what we'll do is we'll take the square matrix y transpose and invert it. And so we're going to, I'll write this in green, multiply here by y transpose negative 1. And to keep this equation true, I'll have to multiply this side also in here by y transpose negative 1. But now the benefit is that because we have here y transpose and y transpose inverse, these two terms will cancel out to give the identity, leaving just L on this side of the equation. And so we'll arrive at our final solution, L equals xy transpose times the inverse of y transpose. Any questions on this? All right, so this technique is called least squares, and it's very, very common in linear algebra and machine learning. It's enabled a lot of modern regression, and so this is a very classical technique going back to Gauss in the 1800s. And so one more final word on least squares is that this matrix y transpose times y transpose negative 1 appears so often in linear algebra that it has its own name. It's called the pseudo-inverse, or sometimes we just call it dagger. And so we'll call this term y transpose, inverse y transpose, y dagger. And the reason that it's defined is because if you'll remember, we had our x equals Ly, and we wanted to just invert y, but we can't, strictly speaking, invert y. And so what we'll do is we'll pseudo-invert y. And so then this equation will have a natural solution. L is equal to x, y, dagger. And so this pseudo-inverse allows us to just take matrices which aren't square and maybe aren't full rank, although you don't have to worry about this for this class, and just bring it to the other side by multiplying it by its pseudo-inverse. All right. So just to recap, to come up to a high level, our matrix of x's were the monkey's reaching kinematics, his x and y velocity across all time. And this y was his neural data. And so the bin spike counts across all time. And all we did was we said, take all my velocities across all time, and then multiply that by the pseudo-inverse, this matrix here, of all my neural spike counts. And from that, I'm going to get an optimal L. And this L is going to allow me to decode. So now, how do you do this in MATLAB? It's really, really simple. Like we said, you're going to fit these with just a few lines of MATLAB. All you'll do is, in MATLAB, you're going to literally have a matrix X, which is your reaching kinematics. So we're going to give you monkey's kinematic data, and you're just going to calculate his velocities at time 1, at time 2, all the way up to time k. And similarly, you're going to bin his neural data into this matrix where this is the bin spike counts for the first 20 milliseconds, the bin spike counts for the second 20 milliseconds, all the way up to the end. And then all you have to do is you have to call L equals x times y transpose. This apostrophe is how we transpose matrices in MATLAB. So x times y apostrophe times inverse. This is the inverse of a matrix command in MATLAB. Y times y apostrophe, y transpose. Alternatively, you could also just use the pseudo-inverse command, which is p-inv, and you would just call L equals x times p-inv of y. And so one thing that I forgot to do was to check that all the dimensions here work out. And so if you were to work that out on your own, we know that y transpose is a 97 by 97 matrix, right? I'll do it actually quickly right now. X here was a 2 by k matrix. Y, you'll remember, was 97 by k. But because we transposed it, we flipped the rows and the columns. And so y transpose becomes k by 97. And then this y transpose negative 1 is 97 by 97. And so if we were to perform this matrix multiply, we can see that on the inside, all these terms are the same. And we would get out a 2 by 97 L, which is exactly what we said the dimensionality should be. All right, everyone clear on how to fit this L, given you observe training data X and neural data Y, kinematic data X and neural data Y? All right, so how do we decode with this then? Now that we know L, we can decode incoming neural data. So in the previous setting, we had observations of the kinematics and the neural data. But when we decode, what we want to do is we want to translate the neural data into new kinematics. And so variable do we not know? Yep, x of k. So, so now let's call y tilde of k our incoming neural data. Why is there a tilde over this y of k? Why isn't it just y of k? Yeah, it has the one term at the very bottom. Great. And so L is a matrix that we know. L we just learned from our training data. So we now know what L is. And then y tilde k is this new incoming neural data that we have. And then as Adrian just said, we append a little 1 at the bottom to account for the constant. And so then to decode new kinematics, we just multiply these two matrices. So this is known, the L is known, and the y tilde k is known because we just observed this incoming new neural data. And then based off of that new neural data, we can calculate the velocity that the monkey was intending to reach to. And so now xk is known, and we can decode that velocity and update the cursor and then show it to the monkey. And the monkey will be controlling this with his neural activity alone. And so a brief aside is that when we find L in this way, it's actually no longer called a population vector. It's called an optimal linear estimator. And this term was coined by Salinas and Abbott. Abbott is the same guy who wrote your text, the chapter 1 of that spiking rate statistics book that we handed out, chapter 1, 2. And the reason it's called the optimal linear estimator is because this technique to find L does something very important. It minimizes the squares of your error. So you don't have to know why this happens, but I'm telling you that if you have your big matrix X and your big matrix Y, the L that you find through this means will minimize X minus Ly squared. So again, we said that L doesn't do a perfect job at making this 0. This will not go to 0 because the system is overdetermined. But there'll be some errors. And if we square those errors, it turns out that the L that gives me the least squares error, that's why it's called least squares, is of this form. And so because this minimizes your errors in the decoded kinematics, Salinas and Abbott called this the optimal linear estimator. And so this way of finding this population vector-like algorithm is actually a bit better than the population vector, because in the population vector, we found all these di's separately, the bi separately, the alpha I separately. And so if you have this technique, you would actually never want to use a population vector, because this is always going to be more optimal than a population vector. All right, so how does this decoder do? So I'm going to show you a video now. This is a live video, or a video from an online experiment where Monkey J controlled this population vector / optimal linear estimator. And all we're doing here is we're decoding the velocities with the incoming neural data using the L matrix found exactly as I've told you. So you can see it starts off sort of good, and it's a bit jittery. It seems to have trouble going up and to the right. And sometimes because it's so jittery, it'll fail to acquire targets, and the monkey will get frustrated. But it doesn't do bad. Its success rate you see is 60%. Actually, that is pretty bad. But we can definitely improve that. But the monkey is doing a valiant job to control this cursor. So one thing you'll notice is that the cursor was pretty jittery, moving around with like sort of a micro jitter. Can anyone tell me why that is? So in these previous videos that Professor Shenoy showed, the cursor was really nice and smooth, moving all over the workplace. But this one jitters a ton. Anjali?
There's no smoothing parameter involved?
Yeah, exactly. So what we're doing is we're decoding the velocities, the xk's, only using neural data at yk. And what do we know about neural data? Neural data is, yes, it's extremely noisy. Or not, neural data is noisy. It has Poisson-like statistics. And so even if your rate is, say, 40 spikes per second, you guys know from your homework that if you bin the data at 10 milliseconds, even if it's at 40 spikes per second, and if we plotted this on a time versus rate versus spike count axis, and this was 40, we would see values that looked all like this, right? You guys remember all these messy histograms from your homework. And so this yk is really noisy. And we're decoding the velocity based off of only the neural data at time k. And so if the neural data is noisy, my velocity estimates are going to be noisy. And because my velocity estimates are noisy, it's going to cause this cursor to just jitter around all over the place. Does that make sense to everyone? All right, so we're going to try to make this a bit better. And what we're going to do is we're going to take our neural data, and this time we're just going to smooth the neural data with convolution by a Gaussian kernel. And a Gaussian kernel has a standard deviation of 100 milliseconds. So what does this mean? If we were to just draw a Gaussian, the Gaussian kernel would look like this. And this is its standard deviation. And this can be time. And so the wider the standard deviation, the more we smooth our data. Now, there's a little subtlety here, which is when we smooth our data, right? If we were to flip and drag, we know that convolution is flipping this and then dragging it, right? And so if we were to flip and drag this, we would actually be trying to smooth future data if this is centered around 0. And so to make this Gaussian kernel causal, we'll actually smooth with a trace that looks like this, where this is the same standard deviation. But this will be a causal filter, right? Because now when we flip and drag, if I were to flip this signal, here's flip, it would look like this. And so it's not smoothing in any data into the future. It's just smoothing data in the past. So this is your classic EE102A doing convolution by hand. And so what we'll do is we're going to smooth the data, all the neural data, by just convolving it with a Gaussian kernel. And this is its performance. So the monkey still has trouble going up and to the right. But you'll see that the cursor is a lot smoother. And eventually, he can sometimes hit these targets up and to the right. He'll get to a success rate of, say, 80 to 90%. And so we've used the exact same algorithm. All we've done is we've smoothed our neural data, taken into account history, and that increased our success rate by almost 25%. Yes, Anjali?
What design selection or holding or
So the target is selected when the monkey holds the cursor still over a little acceptance window around it for 500 milliseconds.
Thank you.
Yep.
So if the monkey in this case is having difficulty moving upward to the right,
Yeah.
would that mean that most of the neurons that you're collecting data from have a preferred direction that's downward and to the left?
That's exactly right. Yep. Yeah, and so you'll be playing around with this in homework 4. In homework 4, what you're going to do is you're going to plot the preferred direction of the top 30 neurons, and you're going to see if there are any gaps in where the decoder might be able to be controlled because there's a lack of neurons in that direction. All right, so from this example, we see that history helps. And no surprise, we know that convolution by a Gaussian kernel is like low-pass filtering, right? So if I had my noisy spike trains that looked like this, and then I hit them with a low-pass filter, I might get something that looks like this in blue, something a bit smoother. And that smoother signal that we decode off of leads to less of this jitter in the kinematics. And so it seems like history helps. And so now the question will be how to better use history. Yes, Nathan?
So, I mean, it seemed like, there was that one big move where he was able to go up and to the right.
Yeah.
Was the reason that was more successful is because it was so large of a distance, and so he would have to be attempting to move faster, and so we would get a bigger signal? Or, I mean, what sort of cases would you be able to decode that direction more easily?
Mm-hmm. That's a good question. So it is sometimes the case where if you have very little representation up and to the right, if you make these small up and to the right commands, you might not get enough modulation in your neural activity to actually command a velocity up and to the right. Whereas if you have these large reaches, you would modulate your activity even more. You'd command a really large velocity, and that might be able to be decoded better. So you do run into some of these situations. But in general, if it's a smaller target distance up and to the right, it'll be easier for the monkey to do.
So, I mean, why in that case did that one work and not the other ones?
So one thing is that monkey could have tried to go up and to the right. You'll sort of see that on some of them. It looks like he gave up. So what happens is that he could have tried to go up and to the right. But then what happened is that he saw the cursor didn't move that much, maybe because he wasn't commanding as large a velocity. And so he saw, oh, it's not going up and to the right. I'm just going to not try this trial because it's too far away and I don't want to even try anymore. But then and so this is sort of the closed loop feedback aspect of it, in which the monkey sees the cursor, how it's updating, and he'll adjust his strategy as that cursor is updating. And so if he sees the cursor is going up and to the right at a good velocity, maybe he'll be like, OK, I'm going to continue. Now, I should say that this isn't something that happens often. We usually use better algorithms. And so in those cases, the monkey's able to hit all the different targets. And it's in these scenarios when we use poorer algorithms, where he might settle into these regimes where it looks like things are too hard, so he's just going to not even try that target. Gary?
Just a clarification on the convolution. Are we doing a smoothing on the raw data or on the output, on the kinematics?
Oh, we're doing a smoothing on the neural data. Okay. Yeah, that's a very good question.
Is there, like, have we ever analyzed whether it's better to do it on the raw data or like the benefit of doing it on the neural data rather than the output?
Yeah, we'll get to that. So what the Kalman filter is doing is actually basically smoothing your output, although it can be viewed as a smoothing on the inputs. But in general, it's better to, the outputs are very low dimensional, and so in general, it's better to smooth your inputs. And I hope to convince you of that later when we talk about incorporating history. And so before we go on to incorporating history, I do want to say that this optimal linear estimator is the algorithm that was used in that 60 Minutes video where there was a Pittsburgh woman who was controlling the robotic arm. And she was controlling it, and she was able to shake the interviewer's hand. And so they're exactly using this optimal linear estimator. They're actually using a variant that's slightly different, which you guys would understand. Yeah, I'll explain it briefly. And so what we fit was an optimal linear estimator where we did x equals L times y. In Pittsburgh, what they do is they fit an optimal linear estimator where they say y equals b times x. And we know through our handy trick of the pseudo-inverse that we can find this b by just saying b equals y times the pseudo-inverse of x. And then what they then do is they decode data by saying x is equal to b pseudo-inverse times y. So they do this thing, it's called the inverse optimal linear estimator, where they do a pseudo-inverse calculation, and then they re-pseudo-inverse it. But it's almost basically the exact same thing. And so you guys now know how to build a decoder that leads to the performance that you saw of that robotic arm in Pittsburgh. And that's no small feat. Anjali?
Are there trade-offs in the optimal linear estimator versus the inverse?
I'm sure there are. I've actually never tried this. I've never tried this algorithm online, and no one has directly compared them online to my knowledge. And so we don't know exactly which one's better, but I would expect them to be of comparable performance. All right, so when we did our convolution of the neural data to incorporate history, what we've basically done, right, when we convolve is we take a kernel and we multiply in time and add. So what this basically means is that our smooth neural data, we'll just call it yk bar, is equal to some yk plus, let's say, 0.7 yk minus 1 plus 0.4 yk minus 2 plus maybe 0.1 yk minus 3. And all I've done here is, for a Gaussian kernel, I've said that this value here is 1, this value here is 0.7, this is 0.4, and then this is 0.1. And so all we're doing is smoothing data by just adding terms in the history. Classic low-pass filter. And so if I were to decode with the smooth neural data, as we just showed you, that would just be equivalent to having a decoder that did xk is equal to L times yk plus 0.7 times L times yk minus 1 plus 0.4 times L yk minus 2 plus etc. Is that clear to everyone? And so all we've done in this case is treated history by taking our L matrix and multiplying it by some scalar. And this works, as we showed. But we should be able to do something better, right? Instead of just fitting this L matrix and then downweighting it by some scalar factor, I should just be able to fit some optimal L0, some optimal L1, some optimal L2, etc. And so this technique is called Wiener filtering. And all we're doing is the sum is writing exactly what I said before. For p equals 0, we have L0 times yk. For p equals 1, we have L1 times yk minus 1, etc. And so the key here is that when we formulate the problem in this way, as opposed to just smoothing the neural data, we can now optimally know how to weight each term in the neural history to get even better decoding. So let me see what the next slide is. So let me write just the first two terms. Xk equals L0 times yk plus L1 times yk minus 1 plus dot, dot, dot. What's one way that I might find L1? Exactly. So one way that you could do it is you could just delay all your neural activity by one time step and then perform your same optimal linear estimator equation. Right? Does that make sense? So all I've done is I'm now we had big X, which is equal to V1, V2, V3. Now all I'm going to do is I'm going to have I'm going to change big X to be V2, V3, V4 up to Vk. And I'll have big Y be Y1, Y2, up to Yk minus 1. And so now when I do the regression, I'm seeing how Y1 predicts V2 and how Y2 predicts V3. And that would be one way to find L1. But it turns out that this isn't optimal because we're not considering how the data is autocorrelated in time, how it is correlated with itself through time. And so to take this into account, what we're going to do is we're going to fit the Wiener filter. And basically for all least squares problems, we're going to just want to make the same setup, which is we want to write an x wiener equals some L wiener times y wiener. And we want to perform the pseudo-inverse operation, LW equals this XW times the pseudo-inverse of YW. And so now we just have to set up this large sum in this form. And so what we'll do is we'll take this xk equals L0 times yk, et cetera, and we'll write it as this matrix multiply. Right? And so this will equal L0 times yk, L1 times yk minus 1, LP times yk minus p. So what are the dimensionalities of these two matrices? What's the dimensionality of this matrix? How many rows are there? Two? Yep. And then how many columns are there in L0?
P by K.
Oh yeah.
In L0.
Yeah, exactly. So there's 96 in L0. So I haven't added the constant of 1 here. So L0 has 96. And then there are P of them. So it's 96 times P. And similarly, we can see that this big Y matrix here is a vector that is 96 times P. All right? And so we're going to say now this has to hold for all times K. And so we'll just take all of our data and we'll concatenate it again. And if you were to write out this, so for xp plus 1, we would decode with the data at yp plus 1, yp all the way down to y1. And then I'm adding my constants 1 here. xp plus 2 will be decoded with neural data from yp plus 2 all the way down to y2, et cetera. Does this make sense to everyone? All right, so at this point, we've set up our equation exactly as we want it. We have here an xw, our lw, and here our yw. So at this point, we can just fit LW equals this XW times the pseudo-inverse of YW. And there we have it. We've solved now simultaneously for all these L0s, L1s, L2s. And all we've done is we've used the same trick that we've been using, that we've learned today, which is to just write something as x equals L times y, and then pseudo-inverse of y. All right, so this is what the Wiener filter performance looks like with Monkey J. So you can see it's very smooth. It moves directly to the goal. It can get to all different parts of the workspace. And his success rate is 100%. I think there's a failure at the end here, but he in general controls this extremely well. And this is state-of-the-art performance. This is basically similar to that really fancy Kalman filter that we showed you guys earlier. And so, now we've found a way to optimally incorporate history and make our decoders even better. And so this decoder would be even better than that decoder used by the woman in Pittsburgh. Yes?
Is there a way to find like an optimal number of like previous time points you need to use, or what the optimal value of P is?
Yes.
Like that trade-off there?
Yeah, so this is something that I wasn't happy about. But in 2009, there was a paper that came out. And in this paper, they basically said Kalman filter is better than Wiener filter. And they had experiments to support that Kalman filter was better than Wiener filter. But it turns out that for their Wiener filters, they set this history to be 1 second long. And that's a long amount of history. So you can imagine if you're controlling this thing and it's going the wrong way and you say, oh, shoot, I need to make it go the other way. The data is getting smoothed all the way in the past to 1 second. So your commands from 1 second ago are still affecting the cursor today. So what that does is it increases basically the loop time in control theory terms of the decoder. Basically, the latency from your command to the response has this 1 second look back into history. And so that actually leads to a really poor Wiener filter. And so the Wiener filter that I'm showing you here used a history of 250 milliseconds. And there was really no way to optimize this except to have a monkey control this and sweep the history, which is what I did. And I found that any history between 200 and 300 milliseconds is generally pretty good and leads to the control that you see here. And so in a paper that we recently put out, we actually showed that Wiener filter is better than Kalman filter. Right? And I think we're at time, so we'll finish off with just a few more slides in this lecture come Monday. Have a good weekend, everyone.